Hello everybody and welcome to the first Calculus 2 lesson during this whole coronavirus debacle. Since our professor hasn't really gotten back to us as to whether or not we are going to have some sort of online lessons, I figure I would catch you all up to speed on lesson 11.3 just because we have some homework coming up soon. And if I'm not mistaken, I don't believe he's changed the due date for that. But anyways, I'm going to teach you all about lesson 11.3. which is the integral test of series. Oh, and happy St. Patrick's Day if you celebrate, whatever. I don't even know. All right, so going over 11.3, let's say, for example, that you have a series. It starts at some number and goes all the way to infinity. And let's just call this the inside of the series a of n. Now, when we evaluate a series, we can get two results. We can say that it's convergent, or we can say it's divergent. And we can evaluate whether or not this series meets convergent or divergent with a number of tests. And the one we're going to be going over today is the integral test of series. Now, the integral test of series states that if a series, like the one above, is convergent or divergent, and this can be determined by rewriting the series as an indefinite integral. So in rewriting this series, we're going to have the integrand right here, which is this symbol, from 1, which is taken from this bottom number right here, and goes all the way to infinity, which is this top bit right here of a of n. But instead of writing a of n, we're going to be writing f of x. This is just for notation, and so we don't get confused by this. And then dx. So the integral test states that if the following rewritten integrand right here, if this converges, so will the series. And if this indefinite integral diverges, so will the series. Now, the integral test can be performed only if this inside value here of f of x meets the following requirements. The function of f of x needs to be positive, decreasing, and continuous. Let's say, for example, the function y equals 1 over x, which looks something like this. So when you're putting in very small values of x, we're still going to be decreasing and decreasing. However, we're going to taper off and go into an asymptote that approaches 0. So as the value of x increases, our output will reach very, very close to 0, but will never touch it, but it will continue going on to infinity. And so since this function is only located in quadrant 1, it will always be positive. It is always going to be decreasing since we read our graphs from left to right, and it's continuous because there are no values for which this function is not continuous. So our first example, we are going to be rewriting this series right here as an indefinite integral. This is just to get you all started on the process of doing this, because since this is the first step in setting up our entire test. So we're going to rewrite this as the integral. Our lower bound is going to be this value right here, 4, and it goes all the way to infinity, so that will become our upper bound. And anywhere we see a value for n, we are going to simply replace it with x. So this will become 1 over x plus 2 squared dx, just to formalize this integral. And if this integral right here ends up being convergent, then that means this series will converge. And if this integral right here diverges, that means the series will also diverge. All right, going into the official practice problems, example 1, we are going to state whether or not this series is convergent or divergent, and if it converges, state to what value. So our first step, like we did in the previous example, we are going to be rewriting, step number 1, we are going to be rewriting series as indefinite integral. So this series right here is going to be equal to the integral of, our lower bound will be 1, and our upper bound will be infinity, and anywhere we see a value of n, we're going to replace for x, so this will end up being 1 over 1 plus x squared dx. And from here, we're just going to evaluate the indefinite integral like we did a few chapters ago. So since one of our bounds goes to a value which makes this function undefined, we're going to rewrite this as the limit as t approaches infinity from 1 to t of 1 over 1 plus x squared dx. And this is just going to end up equaling the limit as t approaches infinity of arctangent of x from 1 to t. And evaluating out this limit right here, we're going to get the limit as t approaches infinity of arctangent of t minus the arctangent of 1. And so, as the arctangent of t goes to an infinite value, this means that our output will become pi over 2. And as the arctangent approaches a value of 1, it will equal pi over 4. And pi over 2 minus pi over 4 is going to get us pi over 4. So, since our indefinite integral converges to a singular, I should say goes to a single value, I just spelled it right there, it will converge. So, since our indefinite integral converges, that means our series does also. So, by the integral test, it's always good to write out which test you use. The series converges. Let's see, use my pen. Not working. Oh, there we go. It converges. And just to make sure, I'm sure most of the problems we're going to get in our homework and on future tests and quizzes, I'm sure most of them are going to be functions which are positive, decreasing, and continuous. And this only takes a few seconds prior to the evaluation of all of this just to make sure that your functions are as such. And just again to reiterate, if your function is not positive, decreasing, or continuous, then that doesn't mean the function, or the series, I should say for that matter, is automatically going to be divergent or convergent. It just means that you can't use the integral test to prove whether or not it is such. So just looking at this function right here, this function will always be positive since we have a square on the bottom. So that will make any negative value positive. And as the denominator gets larger and larger with every value of x, so your output will be smaller and smaller. And since the numerator is how it is, there isn't really a value of x that would make this an uncontinuous graph. All right. Moving on to the next example, which is the same spiel as last time, we are going to state whether or not the following series is convergent or divergent. If it's convergent, state to what value. So, step 1, we're just going to be rewriting this. So our lower bound is 1 and goes all the way to infinity of x over x squared plus 1 dx. And again, this function will always be positive since it has a square in the bottom, and So the denominator will always be negative, and it will always be decreasing as well, and it will always be continuous. So we're taking this indefinite integral, we're going to be evaluating it by rewriting it as the limit as t approaches infinity of the integral from 1 to t of x over x squared plus 1 dx. And evaluating this, we are going to be using u substitution. So we're going to be taking this denominator here as our value of u. So u is going to equal x squared plus 1, such that we have du equals 2x dx, meaning that 1/2 times du is going to equal x dx. So rewriting this indefinite integral with the u substitution, we're going to be getting the limit as t approaches infinity of the integral of 1 to t of 1 over u times 1/2 du. And just simplifying everything out, we're going to be having 1/2 the limit times of t approaches infinity from 1 to t of 1 over u du. And that's just going to give us 1/2 of the limit as t goes to infinity of the natural log of x squared plus 1, because we're plugging in our u substitution back, evaluated from 1 to t. And now we're going to evaluate the limit to determine whether or not this indefinite integral converges or diverges. So writing this out, we're going to get the 1/2 times the limit as t approaches infinity of the natural log of t squared plus 1 minus the natural log of 1 squared plus 1. And that will give us 1/2 the limit as t goes to infinity. I know it gets kind of old, but we need to keep writing it as of the natural log of t squared plus 1 minus the natural log of 2. Alright, now thinking about this limit right here, as t goes to an infinite value and we square that infinite value, it's just going to be a bigger infinity. And if we add 1 to that infinite value, that will still be infinity. And even taking the natural log of that value, it will still be infinity. And infinity minus the natural log of 2, which is a very small number, will still go to infinity. So our indefinite integral, which goes to infinity, diverges. So, and then just rewriting all this out so it looks really pretty, our series from 1 to infinity of n over n squared plus 1 diverges as a result of the integral test. And again, it's always really, really good to write out which test you use, because on exams and quizzes and stuff, it will just say to evaluate the series as to whether or not it's convergent or divergent, and you have to state which test you're using. And it's just good to get in the habit of, when you're maybe doing these homework problems or, tests and quizzes, that you keep writing which tests you used. It's just good, to keep track and be organized like that. All right, our very last problem, which, yay, finally. We have this series right here of from 1 to infinity of n cubed over n to the 4th plus 4. And if we see this right here, it again follows a similar, pattern to the series that we've seen before, whereas the denominator, as the value of n increases and goes all the way to infinity, the denominator gets very, very large and is divided by a smaller numerator, meaning that this function right here will always be positive, decreasing, and continuous. So our first step, we're going to be rewriting this as the integral from 1 to infinity of x cubed over x to the 4th plus 4 dx. And since this is an indefinite integral, we're going to write this as the limit as t approaches infinity from 1 to t of x cubed over x to the 4th plus 4 dx. And similar to the last one, we are going to be using u substitution to clear out this denominator right here, since it looks like it'll work out really, really nice with the numerator. So we're going to have u equals x to the 4th plus 4, such that du equals 4x cubed dx, meaning that we can have 1/4 times du equals x cubed dx. So rewriting our indefinite integral with the u substitution, we're going to end up having the limit as t approaches infinity from 1 to t of 1 over u times 1/4 du. And just factoring that out, we can have 1/4 limit as t approaches infinity from 1 to t of 1 over u du. Now, solving for this integral right here, we're going to have 1/4, the limit as t approaches infinity, that does not change, of the natural log, and plugging back our u, natural log of x to the 4th plus 4 from 1 to the t. And now we just finish evaluating this out to get whether or not this indefinite integral is convergent or divergent. So that's going to give us 1/4 limit as t approaches infinity of ln t to the 4th plus 4 minus ln of 1 to the 4th plus 4. And similarly to the last problem, when we plug in a value of infinity for t, infinity to the 4th power is going to be still infinity, plus a value of 4 will still remain infinity. And the natural log of that infinite number will still be infinity. And then minus ln, I believe this calculates out to ln of 5. That's a very, very small number again. And even when multiplied by this 1/4 on the outside right here, it's still going to equal, or it's still going to go to infinity. So, just wrapping up our entire problem right here. So, the series from 1 to infinity of n cubed over n to the 4th plus 4 diverges as a result of the integral test. So in summary, the integral test can be used when this inside portion of the series right here is positive, decreasing, and continuous. If it does not meet one of those requirements, that's okay. It just means that you need to use some other form of testing to verify whether or not this series is convergent or divergent. And when it does meet those requirements, you can very much use the integral test. The lower bound comes from the initial value right here, initial value I of the series, and goes all the way to infinity as it's specified in the top part of the series right here. And anywhere you see the value of n, you replace with the value of x, and then you just solve the indefinite integral like we did a couple chapters ago by taking the limit of this series. I know it looks kind of garbled and kind of gunky looking, but it's actually very, very familiar content when, I guess, evaluating what we've already learned this year. And just make sure in your final answer to, again, state which test you used, and if it goes to a particular value, like let's say this entire series goes to a value of 1. Just make sure to state that. So yeah, I hope I helped you guys out. I hope you all are hanging in there during this coronavirus time. So yeah, stay safe, wash your hands, and take care of yourself and your families. Hope you all are doing pretty well. All right, have a good night.